This is on page 240. And this is a question that's a little bit more involved. It says, determine two ways to restrict the domain of this so that its inverse is a function. And just a reminder, an inverse will be a function if the original graph passes the horizontal line test. So we're starting with a parabola. If you draw a horizontal line on the parabola, you hit 2 points. If you hit more than 1 point, that tells us that if we switch x and y, the inverse won't be a function. So what this question is saying, what could you do if you restricted the domain? And what they mean by restricted the domain is right now, the domain of this function is everything. But if you only took part of the domain, could it pass the horizontal line test? For example, and the examples you will be doing are they're like always parabolas. Does it make sense if I only take half of the parabola? I'll color code it. If I take the vertex and call this the blue half, and this the green half. If I only had the blue half, can you see it would pass the horizontal line test? Or if I only had the green graph, it would pass the horizontal line test. So first of all, horizontal line test says if a horizontal line hits your graph more than once, the inverse won't be a function. If it hits it only once at all places, then your inverse will be a function. So when I take a horizontal line, oh, it was horizontal. There we go. Let's take this one and delete it. If I take this horizontal line, if I consider the whole thing, it's hitting the graph twice. But if I only think about the blue part, then the horizontal line only hits the blue part once, no matter where I am. Same thing with the green part. If I think of the green part, it only hits the horizontal line once. So, question number 1. Part 1 of this question says, determine two ways to restrict the domain. I'm going to color code this. First, if I take this part, it would be when x is less than or equal to 1. And 2 would be when x is bigger than or equal to 1. Can you see that the green one is when x's values are less than 1? The blue one is when x values are bigger than 1. Okay? If I took the blue part and I took points on the blue part, can you see that the vertex is at 1, 3? So the inverse would be at 3, 1. I have this point here at 2, 4. That would give me 4, 2. And finally, I have 3, 7. So I would have 7, 3. That is the inverse of the blue section. I could do the same with the inverse of the green section. I would have 0, 4, so I have 4, 0. I would have 1, 7, so I would have, negative 1, 7, so I'd have 7, negative 1. That's the inverse of the green section. Remember, you can find the graph of an inverse by just taking the coordinates and switching the x and the y values. What haven't I done if I read the question? determined two ways to restrict the domain. I've done that. I've used a graph to illustrate. I've done that. The only thing I have left is to write the equation. Okay? So how do you write the equation? What was our algebraic way? We switched x and y. And solve for y. So we've got our original equation. If I switch the x and the y, I would have x equals bracket y minus 1 squared plus 3. Because they gave us the equation right beside the graph and also in the question. And now I have to solve for y. So I'll first isolate this that it's squared, so I'll move the 3 over. I can get rid of the squared by square rooting both sides. When you square root both sides, you get a plus or minus. So I'll have plus or minus x minus 3 equals y minus 1 now. And to get y by itself, I would have to add 1 to both sides. Now, what this gives us is a square root graph. In fact, it gives us so we would have one equation with the plus sign and one equation with the minus sign. And what you have to decide is which equation goes with the blue graphs that we were looking at and which equations go with the green graphs. You can do this in a couple of different ways. One, you can use your transformations. Can you see that this would be a square root graph? You know what that shape is? Right? Here's your square root graph. It would have to move 3 to the right and 1 up. If I took this shape, moved it 3 to the right and 1 up, can you see that that would match with the blue one? So I can now write the equation for number 2 has to be the positive one. If I think about the green one, it got flipped vertically first. How do you have a flip vertical? A negative outside, then move 3 to the right and 1 up. It's all good. So we also had to find the equation. On your take-home quiz, I think it's question on the second take-home quiz that I gave you already. I gave you 2 graphs, so you could do the one graph on one color on one, and then you could highlight the other color on the other one. That's why there's 2 graphs on the second take-home quiz. What question is it? Someone? Yes, number 7. So number 7 on your second take-home quiz is it is just like this. Just the vertex is in a different place. So notice that on my original graph, my vertex is at 1, 3. The x-coordinate of the vertex is what was your domain restriction. Once you've restricted your domain, you still have to find the equations of the inverse. We found the general equation of the inverse by switching x and y and solving, which gave us the plus or minus. And then we had to determine which one went with which. It's not too bad because the minus out front gives you a vertical reflection. So anytime that square root is going the underside part, will always be the one with the negative. And whenever the square root is the normal one, that'll always be the positive one. Okay, so in your homework, you can circle questions 10 and 12.